Okay, so now we look at asymptotic notations, the big O and the big theta notation. Now, given a function say t of n and another function say g of n, if the values of the function t of n after say value n0 are always going to be less than or equal to some constant c times g of n. So something like this. So t of n after n0 or always the values are going to be less than or equal to c times g of n. So then we can say this g of n function is the kind of like an upper bound so of this t of n function. So the values of t of n are always going to be less than or equal to the values of the function c times g of n. So the c is let's say constant. So g of n is what is important to be considered. So we can say t of n is equal to big O of g of n. So g of n is the upper bound function. So the values of t of n are always going to be bounded above by the g of n function. On the other hand, if both the functions t of n and g of n grow at the same rate, just differing by constants, so in the sense that the values of t of n are going to be greater than equal to c2 times g of n, but less than or equal to c1 times g of n, then we can say both t of n and g of n are growing at the same rate. So we can say then t of n is theta of g of n. Okay. So, for example, if you're given say this 2n square plus 3n plus 5, so what can we write as theta is this n square, because this n square function grows at the same rate of this 2n square. So this 2 is the coefficient, is you can discard it. So what matters here is the most dominating term. This is n square term. So this is a polynomial. 2n square plus 3n plus 5. So in this polynomial, the most dominating term is n square term, and that is what is deciding the rate at which this function will grow. And what is inside this theta notation is also an n square function. So both grow at the same rate. Now, can we write this 2n square plus 3n plus 5 as theta of n cube? No, it is not possible, because n cube grows faster than n square. So as now on the other hand, if you look at the big O notation, we can write 2n square plus 3n plus 5 is big O of n square, because by notation of big O, they either grow at the same rate or the big O function grows at a faster rate. So we can write it's big O of n square, or big O of n cube, or big O of n to the power 4, and so on. So as long as 2n square plus 3n plus 5 grows less than or equal to the function inside the big O notation, we can say f of n is big O of g of n. So the growth of f of n is less than or equal to the growth of g of n. So we can say 2n square plus 3n plus 5 is big O of n square, or big O of n cube, or big O of n to the power 4, or even big O of n to the power 2.5 or n to the power 3.1, or anything that grows the same rate or faster than the function f of n. So we can see now, in the case of big O notation, there's no one particular answer. So that is why we say this, the big O notation gives you a loose bound. Okay. On the other hand, the theta notation gives you a tight bound. So for given f of n function, say like in this case 2n square plus 3n plus 5, we can always say it is only theta of n square. We cannot say it's theta of given n to the power 2.1. On the other hand, we can say it is big O of n square, or n big O of n to the power 2.2, or n to the power 3, or anything, right? So this big O notation is then considered as a loose bound, whereas theta is considered as a tight bound. Now, so if you're given say two functions, 2n square and 0.05n square, so obviously after say n is 40, we can say that 2n grows slower than 0.05n square. So we can say 2n is bounded above by this 0.05n square. So we can always discard the coefficient when we write inside the big O notation. So we can say 2n is equal to big O of n square. Okay. Now, if you look at linear functions like this, 2n, n, and 5n, they all grow at the same rate, just differing by constant. So we can say 2n is greater than or equal to n, but less than or equal to 5n. So we can say 2n is just theta of n. So the 2n function and the function inside the theta notation, which is n, grow at the same rate. Okay. So what is the relationship between theta and big O? So if a function f of n is equal to theta of g of n, then we can also say it is big O of g of n. So like in this case, we said 2n square plus 3n plus 5 theta of n square. We can also say it's big O of n square, because for big O, what goes inside the function big O notation could be the same degree or larger. So in this case, 2n square, you can have n square, or anything above n square is also okay for big O. Now on the other hand, if a function say like this, it is say 5n square plus 7n plus 2, we can say it is big O of n cube, but we cannot say it is theta of n cube, because when I use theta, that means the function on the left hand side, which is, what is the function on the left hand side? Is n square function, and what is inside the theta notation is n cube. That's not possible. So they should grow at the same rate if you use theta. If you use big O, as long as your function on the left hand side is growing at a rate less than or equal to the function on the right hand side. So the function on the left hand side is n square. We can say it is big O of n square, fine. We can say it's big O of n cube, fine, or big O of n to the power 4, fine. So as said, it's a loose bound. So again, you can also think about what goes inside the big O is a big guy. It should be the same rate, larger rate, value, degree. Okay. So that is why we say if f of n is theta of g of n, it also implies f of n is big O of g of n. On the other hand, if f of n is equal to big O of g of n, then f of n need not be g of n. So it depends on what is really f of n and g of n. So if f of n is 5n square plus n plus 2 and g of n is n square, then we can say, of course, yes, if this is equal to big O of n square, it's also equal to theta of n square. But if it is like f of n is 5n square plus 7n plus 2 and g of n is n cube, then we can say this f of n is big O of n cube, but not theta of n cube. Okay. So now how we can use big O and theta notation for our best case, worst case comparisons, time complexity stuff. Alright, so going back to the two algorithms that we have seen, so in the previous video you should have seen two algorithms, the sequential key search and the maximum integer problem. So the sequential key search problem, we decided that there is a best case time complexity of just doing one comparison, and then there's a worst case complexity of n comparisons, right? So if the best case is different from worst case, then we indicate the time complexity of the algorithm using the big O notation, and what goes inside the big O notation is the worst case number of times we do the basic operation. So in this case it's worst case big O of n. Now we cannot say the time complexity of this algorithm is theta of n, because as I said, when theta means it's a time bound. So the time complexity need not be all just n comparison. It could be n minus 1 or n minus 2, but these are all n, right? So, but in this case, in the sequential key search, we saw that the time complexity could be as small as this one comparison. So 1 is not equal to n. 1 and n, they are two different functions. They grow at different rates. So that's why we cannot say use theta notation if best case is different from, best case is, yes, different from worst case. On the other hand, if best case is same as worst case, which is the maximum integer problem, so in this case we do what, n minus 1 comparisons, right? So of course n minus 1 is theta of n. So both n minus 1 and n, they grow at the same rate. So we can, again, when I write inside the theta notation, we should discard all the lower order terms as well as discard the coefficient of the most dominating term. So you can simply say now it is state of n, which also means it is big O of n. So always remember theta implies big O, but the converse need not be true. Now another example to make sure reinforce this big O and theta and how to use it combined with best case and worst case. So if you look at the pseudocode here, you're given an input n, and then for some condition, if it is true, then you go inside the if block and run a for loop from I equals 1 to n and print a statement. Okay. Now, so if that condition is not true, you go to the else block, and what we have here is a nested for loop for I equals 1 to n, and then for each value of I, you run a j loop from 1 to n and print a statement. So if you look at the time complexity here, the basic operation here is printing. Okay, so that is what you do repeatedly. Now, how many times we print? It depends whether the condition is true or not. If the condition is true, you get into the if block and you just run one for loop. It means then for each value of I, you print the statement once. So you totally print n times. Now, on the other hand, if the condition is false, you get inside a nested for loop. That means for each value of I, you run a j loop. That means you run n times n square. You do printing n squared times, because for each value of I, you print n times because of the inner j loop. Then I runs from 1 to n, so you totally basically print n squared times. So we have here the best case different from worst case, because the best case is when the condition is true, you print n times, and the worst case is the condition is not true, you print n squared times. So if you put things together, the overall complexity of this algorithm can be denoted only using the big O notation, because best case is different from worst case. And what goes inside big O notation is the worst case time complexity, which is n squared. So we say the time complexity of this algorithm is big O of n squared. Now remember, you cannot say it is theta of n squared, because when I use theta, it should be a tight bound. That means the algorithm should always run something corresponding to printing n squared times. And we see in this case it's not. As a best case, it could just print n times, and n is different from n squared. They go at different rates. So you cannot say it is theta of n squared. We have to say it is big O of n squared. Alright, so we stop this video with this.